The plan for this talk is going to be sort of as follows. First of all, I would like to introduce nuclei as sort of alternative sensors, in a sense, which are much less exploited than many other things, than atomic matter, essentially. And in particular, we'll be concentrating on using this for searching for new interactions at sub-micron scale. I'll explain a little bit more why. But there is a more whimsical point of view here, and that is to say, somehow we haven't really, there is this fantastic technique that has been around for 40, 50 years. And then, as I like to say, chemists have appropriated it, and it's time for physicists to reclaim Mossbauer spectroscopy as a tool for doing physics, actually. And there's actually a number of reasons. First of all, nuclei are really nicely, as was mentioned this morning by others, nicely isolated from many other external interactions. And so they don't feel many backgrounds that other things, that atomic matter feels. But in addition, once you start dealing with nuclei, you also get access to other interactions, like strong interactions and weak interactions, which generally are not exploited in technology, maybe except for nuclear reactors or this kind of things. There is, as I'll show you in a minute, a fantastic range of lifetimes and therefore natural line widths that become available down to essentially less than 10 to the minus 25 gamma over E. And then finally, there is another connection, which again, I'm saying this is really not very rational. It somehow is a little bit dreaming, but there is essentially the fact that in recent times, people have started exciting those transitions not by feeding down with some electron capture reactions or beta decays, but in fact using directly exciting the transitions with synchrotron light. And this has been made possible by, I don't know, third generation and more intense synchronous light sources. And so this opens all sorts of interesting possibilities, some of which have been kind of explored, but many of them have not been really explored. And and this has connections again with things like the clock transition in thorium, which is essentially a Mossbauer transition, except in the optical regime, or maybe slightly inconvenient optical regime. So I think there is a real coincidence of various different things, and having some exploration along those lines, I think is very timely. I will concentrate on just the two red items. First of all, the application to searching for new interactions at microscale, and then a first result, which is actually a paper 1 day old, that is essentially addressing or trying to attack some what I like to call nuclear quantum optics sort of topics. All right. So first of all, a little bit of motivation for gravity. We generally assume that the inverse square law of gravity is valid all the way down to the Planck scale. And since gravity has only been tested really in a lab down to maybe 50 microns, well, that's a hell of an extrapolation. So as an experimentalist, I say, well, okay, I better check this. And then we'll see that from the theory end of things, there is also some more motivation, but I'm happy enough in just saying, that, we need to try to do something about this. Generally, although this is not necessarily the most general way of doing it, but generally people parameterize deviations from the inverse square law of gravity, whether they are because of gravity that behaves differently or because there is a new sort of interaction, by adding a Yukawa term with the strength of it, that is this alpha, and then the lambda that is essentially the scale of the cutoff above which gravity becomes what we are used to. And if I parameterize this way, I have two free parameters, lambda and alpha, and you can represent our knowledge in this alpha lambda plane, where for each lambda, if you want, which is conveniently shown in meters up on the top and in astronomical units down here. For each alpha, you can tell, or you can show from this curve how well we know, down to what level we have tested things. Okay, and so the gray area is excluded by experiment, and the white area is wide open. I mean, you can spend lots of time on this thing. There's lots of different techniques you can see, going from spacecrafts all the way to lab scale things. But we will just concentrate on this area here. And in fact, I'm blowing up now things going from essentially, say, an angstrom or a fraction of an angstrom to a micron or so. And in our labs, we are essentially trying to cover or to invent new techniques. And the shaded area here mostly has to do with torsion balances. There's some other techniques, but most of this thing, if nothing else, has to do with essentially mechanical springs. And the idea is to actually try to address this with different techniques. So we have a program which is not really to be discussed here, with microspheres as force sensors. Then there's some neutron scattering, of some exotic version of it, of neutron scattering. And then in this intermediate range, which goes from, say, a micron down to maybe 10 nanometers or so, is the area where we want to try attacking things with Mossbauer spectroscopy. And keep in mind that having some overlap that shows here is good, because those experiments are all really tricky, and they're all dominated by systematics, old ones, new ones, you name it. And so if you find something, being able to reproduce it with a very different set of systematic uncertainties is, of course, very desirable. So the real challenges, if you do a mechanical measurement, is that the force is really small, and the smaller the distance, the smaller the force becomes. And more important here, when you go to distances which are a small fraction of a millimeter, electric charges are always, or electric interactions are always problematic. And that's because essentially there's always polarization. Even things which are very neutral, they have dipole moments, and if there is a little bit of a gradient of electric field, you get in trouble. And so the idea is that Mossbauer transition, nuclear physics is more immune to those kind of things. And the way to do the measurement is not to measure a force, but to essentially check whether the nuclear potential is modified by this external potential that is acting on nuclei. And so of course, you need to do nuclear spectroscopy with very high resolution. And the way to do this is to use Mossbauer spectroscopy. And here I have some examples. The most common isotope used for this is iron-57. And this thing has a gamma over E that is of order 10 to the minus 13. The first four of those transitions have been, are used, or to some extent have been explored, and they go down to 10 to the minus 16 or so. But there are those monsters here that no one has ever seen, for which no one has ever seen the resonant absorption. And you can see that in some cases you go down to 10 to the minus 25. We have no idea how to actually see the resonance in those cases, but that is one enticing reason to start working on some of those things and see. And just as a comparison, others today have talked about the Q of those cavities is 10 to the minus 6, which is fantastic. This is 10 to the minus 25. Okay, LIGO doesn't, which with its many kilometer arms, doesn't get that far down. So it is, I think, generally very interesting to look at those things. All right, so how does the experiment work? Well, it's actually, you do the usual undergraduate lab Mossbauer spectroscopy experiment, where you look at the resonant absorptions of photons that are emitted by with a narrow line. There is an absorber, and then there is a detector, and you do absorption spectroscopy. And then, as is customary, you use essentially Doppler shift to scan the line, the line of the resonance. It turns out that for some reason this sketch shows that you're scanning the absorber, but you scan the source. But that's sort of not an essential thing. Now, in addition, though, what you do is that you essentially bring something that I call the attractor. That is, you bring very close to the nuclei of the absorber something that you want to test whether it's interacting or it's producing a new interaction, whether it's gravitational or else. And then you look at the line position with the attractor nearby or the attractor far away. And okay, so that's essentially, so it's kind of a new concept of a measurement because you're really measuring this potential, you're not measuring the force. And one thing to point out is that there is nuclear physics in the way. So if you find an effect, it's a great discovery, no matter what. But then to tie that effect to the new interaction, well, that requires some work in nuclear theory that is going to, but in some sense, you know, my other half, the other half of me does neutrinos double beta decay, which is exactly the same situation. We always advertise this as saying, well, you know, if you find neutrinos double beta decay, it's a great discovery. Now, what that means in terms of effective Majorana masses, well, that's complicated, and we don't really know. Okay, but we're after great discovery, so that's good enough. So the first thing is that, okay, so you need to bring those two, actually, let me skip this. So the simple way of doing this at first order is to essentially start with not having those two things as discrete things, but have a substrate, which is presumably has to be thin enough so that it's transparent to the to those gamma rays, which are of the order of 10 keV, actually 14 keV for the iron. Then you deposit a film of your favorite absorber, again, iron 57 in our first iteration of the experiment. This has to be thin enough so that you're testing a particular distance. If you make it too thick, now you're washing out the concept of distance. Then you actually start depositing something like, for instance, gold, and you deposit very little of it just to isolate the iron from the material science point of view from what comes on top. And then on half of this thing, you deposit a much thicker layer of gold, which now acts as your attractor. Now, you could imagine replacing this with, say, aluminum or something, and that's one of the many things that one can do. Again, if you see an effect, you probably want to repeat it with various other sort of intermediate decoupling films. And I'm going to skip this again. Okay, so, and in fact, I'm going to skip this too because I want to talk about something else at the end. So this is actually a typical line, and this is actually real data, just preliminary data. And now, unlike a regular Mossbauer experiment that a chemist would do, where you want to really scan the line and from the shape of the line and how many absorption peaks you get, you discover something about the material science. Here you want to just measure where the resonance is. So essentially, you measure basically 1 point, 2 points of the two sides of the resonance, and then you study the position of those 2 points as you change the conditions and see whether the line moved. Okay, and so you actually really would like all of your statistics to be at the right places. So it's kind of a special spectrometer that is essentially a two-velocity spectrometer. It is not a scanning of velocity, and so we actually have our own thing that we built sort of just for this. And in fact, you can actually do, check. Remember, this is essentially, there is the only case in which a system like this was used for fundamental science or physics was actually for the famous Pound and Rebke experiment of early 60s, where they measured essentially the gravitational blue shift and red shift of photons in the gravitational field of the Earth. And the sensitivity of that experiment is actually shown here by this dashed line. And we've been essentially exercising our system with a relatively weak source. I forgot, this is a 5 millicurie source. In orders of, in times of the order of a month, the thing still, you gain sensitivity with statistics as you accumulate statistics with square root of time, which is good. It means that there's no systematics in this kind of test at the level we reached. But we need to go down a couple of, and so you see we vastly exceeded the sensitivity of the Pound-Rebke experiment, but we need to go down another couple of orders of magnitude, which will be done mainly by integrating longer and having a much hotter source. So having a hot source, and in fact, we'll start running with a 50 millicurie source. That requires a special detector because you start getting lots of pile-up problems. And we're lucky to have SLAC nearby, where they make their own special detectors for synchrotron light for very high intensity. And we have one of those multi-channel detectors that's been tested at this point, and we can use for the experiment. So in this case, you're actually really brute forcing it. You just have many, many pixels. Each pixel takes a small solid angle, and so you can actually get a high rate that way. So the experiment is essentially ready. The main systematic has to do with drifts in temperature, in particular drifts in temperature difference between source and absorber. And so the entire thing is contained in a big, heavy block of copper with lots of temperature sensors and differential temperature sensors. And so essentially everything is ready to go. There is a poster on this. The only thing we're missing is the source. It turns out that there's only one place in the world that makes those things, and that's in Russia. And it's kind of, it's not illegal to buy sources there, but it takes forever. It's kind of complicated. So, and we need a slightly exotic cobalt-57 source. So now I'm going to spend the last 10 minutes or 5 minutes, actually telling you about this nuclear quantum optics result, which is a real result. So the idea is to actually, I said, you scan the source with respect to the absorber. That's the standard way to actually use Doppler shift to actually scan a line. If you scan very fast, something different happens. And so you can see it here. There is a source, and I have the absorber here. But the absorber is actually coated on top of a piezoelectric slab of quartz. And then you essentially use a transducer to essentially excite a propagating acoustic wave through the quartz. And so this essentially vibrates the iron. And so now you look at the at the absorption line from the other side. But the idea is that what you do is that you vibrate the iron at a speed or at a period which is faster, substantially faster than the lifetime of the state. So now you actually generate sidebands instead of doing scanning smoothly the frequency. And so that's actually what happens here. I'm going to show you the result of this. In this particular case, we're actually exciting, the acoustic wave is about 100 megahertz, which is somewhat confusingly about the spacing between originally the hyperfine lines of the iron 57, but that's sort of just a slight, you produce some degeneracy, it doesn't really matter. This is actually the surface acoustic wave thing that was a device that was made in-house. And this is tuned at this 100 megahertz specifically, but you can make a broadband device later on. And so now, okay, so this is the spectrum of the original iron 57 in an iron matrix. So it's got the many, the hyperfine split 6 lines, which are kind of standard for iron. And so now you actually start vibrating at, increasing the amplitude of the surface acoustic wave in there. And you see that you start generating sidebands. And eventually, when you're very high amplitude, you make so many sidebands that they're all way far away. The integral is to be conserved, so each peak is essentially invisible at this point because the absorption is spread over a very, very broad range. So this is essentially an acousto-optic modulator where optic is for X-rays or for gamma rays. So this is sort of, in terms of a device, is kind of a new thing, and there is a number of things we want to do with it. Next, go into a synchrotron light source to do this. And so, you can actually predict exactly how much power, but strength of those lines goes in those lines as you move away in various sidebands. There is a new preprint, as I said, that was posted yesterday, so it's brand new on this. So the conclusion of this is that in the last 2 years, thanks for the support of the foundations, we actually ramped up a program to attack fundamental physics in a very new way, which may or may not pan out. And the techniques are really the interface between AMO, nuclear physics, synchrotron radiation. So it's kind of really exciting. We're learning lots of things, making many mistakes. The first experiment for new interaction is about to be to start. And there's probably going to be many other things, including by playing with those new techniques of nuclear quantum optics. And so I'll just stop by showing people who did the work. Actually, they're all here, at least the ones who are still in the group. And you know, they'll be you know, showing you the posters if you want to go there. Okay, thank you.
Thank you, Giorgio.